Okay, so we're looking at number 59 in Chapter 7 of Serway and Jewett. And it looks like we have a 6,000 kilogram freight car rolling along rails with no friction. And it's brought to rest by a combination of two coiled springs as shown in the figure. So it looks something like this. You got a big spring there and a smaller spring inside of it. The big spring has spring constant K2. Little spring is spring constant K1. Right, and we know that K1 is, and we know that the first spring compresses a distance of 30 centimeters. We'll call that X1 is 30 centimeters. The distance that the first spring compresses before the second spring comes into play. So we know our first distance, we'll call that X1, 30 centimeters, right? So 0.3 meters. And then we know the car comes to rest 50 centimeters after first contacting the system. So we know that our X total, right, the total distance that the springs get compressed is 50 centimeters. Right. And the other thing, it gives us a graph of total force, right? The net force in newtons, that's an F, and versus the distance in centimeters. And it looks something like this. It goes up with a shallow slope when there's just one spring up to 30 centimeters, and then the slope gets steeper since there's two spring constants, K1 and K2, up to 50 centimeters. So how are we going to find the initial speed? So now comes the all-important step of categorizing the problem. We need to figure out which principle to apply to figure out the initial speed. So we look for clues in what we've been given. We know that we're looking for the initial speed, so maybe our first thought could be kinematics, but it's not a constant acceleration, as you can see by the force graph. A better thought would probably be kinetic energy, right, for our initial speed. That'd be we could get that from the kinetic energy the train has before it collides with the springs. There's two equally good ways to look at this problem, actually. We could look at it from the point of view of the work energy theorem, the final kinetic energy minus initial kinetic energy equals the work done on the system by an external force. In this case, the spring. The train would be the system. Right. This one is in the case of the system that we're considering is the train only. And then in that case, the spring is a force, an external force outside the system doing work on the train and changing its kinetic energy. The other way to look at it is if the system is the train and the springs. In that case, the force is internal to the system, and we have a potential energy associated with the system in the form of elastic potential energy. And in that case, mechanical energy is going to be conserved. So our initial kinetic energy is going to be our final elastic potential energy. Right, when it comes to a stop momentarily, the springs are compressed. All the energy is stored in both of those springs. Right. So you'll see we'll get the same answer, whichever approach we try. Right, and either of those approaches should jump out at us because in the case of the work kinetic energy theorem, we know that we have a graph. We see that we have a graph of force versus displacement, or force versus an x, and that should always jump out as us as work because work's the area under that graph. And of course, the conservation of mechanical energy, we have springs, we see spring constants, so that should jump out at us as well. So we're going to try both these approaches. For the train-only system, right, the outside work done, our final kinetic energy is 0. So we're just left with 0 minus our 1/2 mv initial squared. And that's going to be equal to the work done, which is the area under the graph there. And if we look at the graph that the problem gives us, we know that this point over here was at 500 newtons, and this point over here was at 1500 newtons. So to get the work done, we need the area under the graph. I think the easiest way to do that is if we break this up into two triangles and a rectangle, right? So we'll do this triangle plus this rectangle plus this triangle. So the area triangle 1 there is going to be 1/2 times 30 centimeters. I'll put this in meters. Times the height is 500 newtons. Plus the area of this rectangle here, this is a width of 20 centimeters by a height of 500 newtons. Plus this third triangle here, or the third shape, the second triangle, which is going to be 1/2. The base there is from 30 to 50, so 20 centimeters. The height of this triangle is from 500 to 1500 newtons, so that's 1000 newtons. All right, so we can figure, you can do the math and figure out what initial speed that gives you from there. Going on to the other side, though, to see if you can see if we'll get the same result, right? The initial kinetic energy, so 1/2 mass times V initial squared, is going to equal our final elastic potential energy, which is just going to be, and some of that energy is stored in spring 1, and some of that is stored in spring 2, right? So we have 1/2. Some of the energy is stored in spring 1, right, K1, which has been compressed the entire 50 centimeters, right? That's X total squared, right? That's the potential energy stored in spring 1 when it's compressed at all 50 centimeters. Not K initial, sorry, that's K1, plus the energy stored in spring 2, 1/2 K2. That one's just the distance that X2 is compressed, right? So X2 squared. Right, that's this distance. Right, that's X2, which we know is 20 centimeters. Right, or we can figure out from 50 minus 30, obviously. Right, so I left that one symbolically, but you know all the values. You know X total is 50 centimeters and so on. You know K1 and K2. So I'll leave it to you to go and figure out, or go and show that you do get the same value for the initial speed, whichever approach you use. There you go.